Good evening, Year 11. Thanks for coming, guys. Nice to see you all. I've got like 7 people waiting. I'm so disappointed. Okay, so today I'm going to be as quick as possible. I'm going to go through the specimen paper. I do want to let you know that this was one of the, in fact, it is the hardest paper one that I've come across since starting teaching. It is incredibly difficult, and the questions are at a very high level. I will go through each one of them as best I can to try and offer some explanation as to why they're a little bit harder than usual. It's also nice to compare it to the previous specimen paper, which was much more straightforward. They're going to give you a paper that's somewhere in between the 2 papers. So it's nice to contrast them and to talk about the different levels of the questions, and hopefully be able to gain some insight into the kinds of questions that they're going to be asking you for your new 1 to 9 specification. Okay, so let's move on as quickly as possible. I'm going to share my screen with you guys and drop straight into your paper. Okay, so obviously, surname Mr. Duncan, other names King of Chemistry, obviously. So let's scroll straight down and drop into question number 1. So really lovely to see Edexcel pushing you guys a little bit beyond your normal routine of these papers and making you having to think a little bit more outside the box and trying to make the chemistry go a little bit further, bearing in mind that chemistry is always advancing and there's new discoveries, and the example of new elements being created is such a lovely addition to the GCSE papers. So question number 1, new elements can be made by scientists. One new element has recently been given the name nihonium. The atomic number of nihonium is 113. Now, it's really nice at this point for me to drop to the periodic table that you guys were given. Now, I apologize for this being, do you know what I'm going to do? I'm going to insert a picture, and I'm going to take the periodic table I've got on my desktop, because, of course, I mean, I use it on such a regular basis that definitely worthwhile adding that. I've no idea. That's funny. I just inserted that image and I've no idea where it's just gone. Let's try that again. Cool. So there we go. So the periodic table that you guys are given, and it ends, what's really lovely about this question is that your table, of course, ends at 111, and they've decided to go for element 113. Now, element 112 would be here, and they're telling you that nihonium fits in here. It's nice to see that it drops into group number 3, but pushing you that far is definitely something that's new to Edexcel. They don't usually push you as far as that. Oh, it's inserted it there. So the first question, it then says it gave you, of course, the atomic number. And recognizing that the atomic number comes from the definition, it is the total number of protons in the nucleus of an atom. So atomic number, it's nice to just pull that off and go total protons. And I, of course, always write down protons as P+. Total protons in nucleus of an atom. So, and of course, at that point, it drops into your A, B, C, and D. Nihonium has an atom that has 113 protons. And there's our correct answer. Just to confirm that the others are wrong, that a nihonium atom has 113 neutrons. That definitely won't be true. One of the things that you pick up from the periodic table is that as you move down the periodic table, at the beginning, such as carbon, it has 6 protons. And of course, if you take the top number being protons and neutrons, it's got 6 neutrons as well. But as you move down the periodic table, as you move across it and you move down, you get further and further down, and you need more and more neutrons to hold it together. Sorry, I won't be able to attend this webinar. No problem. That's fine. You can study for French, Johannes. No problem at all. So definitely not the neutron number. Nihonium has a relative atomic mass of 113. That's not true either. That's the top number. That's the total number of P's and N's, so it's not that one. Nihonium is a non-metal. Now, that's actually a really nice one to just quickly look at, because one of the very first thing that you guys pick up from the periodic table in year 8 or 9 is the divide line. So if I just quickly draw on the divide line, we know that all of these guys are metals over here, and these are the non-metals. So when does nihonium fit into on this? Nihonium fits in down here at element 113, and it's definitely on the metal side. If we were going to draw on the next line and continue it down, that's where it would be. So it definitely classes still as a metal. Okay, next. So it's definitely not a non-metal. It just confirms the top one. Okay, nihonium, I thought this was a lovely one, and it was nice for them to show the extra bit of detail. Nihonium is placed in group 3. Now, we all know that the periodic table is divided into groups, which are the columns, and the periods, which are rows. And the groups, of course, tell you the number of electrons in the outer shell. So state the number of electrons in the outer shell of nihonium, and that is, of course, 3. If we were going to look at the shell number, it'd be this is a lovely addition, and I can imagine them doing this. And that is, if you wanted to know the shell number of nihonium, it would be shell number 1, shell number 2, shell number 3, shell number 4, shell number 5, shell number 6. So nihonium is going to have 7 shells of electrons in total. Periodic table is a beautiful piece of kit. It allows you to do so much from it. Once you start to get to grips with that, it's just super useful. Okay, next. State why nihonium has been given the symbol as NH and not N or nickel, N or Ni. And the reason, of course, I put the fact that the symbols have already been taken. And you can expand on this and happily say that the N is nihonium based on Japan. Tiffany, I have absolutely no idea. Are you saying that the word nihonium has some kind of Japanese basis? I don't know. Those elements at the bottom of the periodic table are ones that I will have very, very limited knowledge of. So N, of course, is already used for the element nitrogen, and Ni is already used for the element nickel. So I've simplified it by simply stating that they've already been taken. But it would have been nice, in fact, to go on to say, I should have expanded and said that N is already used for nitrogen. I always like going that extra mile. And the Ni is already used for nickel. But the already used thing is clearly the point here that they're trying to make. It's nice for me to mention other elements. Other elements include iron. So iron has the symbol Fe. And the reason why it's Fe and not I, well, of course, we all know that I, of course, is the symbol for iodine. Why is it not IR? Well, that's going to be iridium. It's nice to just be able to pick up elements that are rather unusual. There's iridium and there's iodine. So why do they use the symbol Fe? And the reason why is because it comes from the Latin name for iron, which is ferrous. It's just nice to go that extra mile. Because Nihon is Japanese word for Japan. Do you know what, Tiffany? I love that you know that. Do you know what? Tiffany, you can do me a favor. Can you Google and just see whether or not nihonium was first produced at a collider in Japan? I wonder whether or not that would be true. I can imagine it could be. Okay, nihonium has many isotopes. One of the isotopes is NH286. State what is meant by the term isotope. Right, guys, I'm just quickly picking up on a key mistake that lots of year 11s are making, and that is to forget. Lots of students are discarding this bit, atoms of the same element. And that is actually really, lots of students are simply saying they have the same number of protons and electrons, but different number of neutrons. But what we really need to include here is that they are atoms, plural. This is important. That S needs to be there. This is atoms of the same element with the same number of protons and electrons, but a different number of neutrons. Next, how many neutrons are there in nihonium-286? At that point, you've got to extract data from both of these questions. That's quite hard work, that. You have to realize that they have already told you in question 1 that nihonium has got an atomic number of 113 and that the atomic mass is now 286. So this is the proton number and this is the proton and neutron number. Notice that I do not put a charge on the neutron. What that means is I'm going to quickly run the calculation of 286 minus the proton number, which will give me a neutron number. This question comes up on a regular basis about an element which is not standardly asked for. So tricky. Oh, it was discovered by a Japanese scientist. Thank you, Tiffany. I love the additional information. I will add that to my repertoire of knowledge. Thank you, Tiffany. That's awesome. Next, gallium. I love that they drop you into another unusual element in group 3. Gallium is another element in group 3. Gallium, of course, has a very historical background. Gallium was named after a French chemist, and the word Gall, G-A-L, Gall means is something to do with France, and also I think it also means Lecoq, which is the surname of the scientist who discovered it and extracted it, and he wanted to get both his name and his country name in there. So gallium, group 3, has 2 isotopes. Okay, so first thing is, let's extract the data. We've got gallium 69 at 60%, and we've got gallium 71 at 39.9. The usual routine, this was absolutely bog standard, but they're giving you an element which they're not commonly used. Some people make gallium toys for kids. Yeah, that's really unusual because it melts in your hand. I wouldn't say it was for kids. It's more for demonstration purposes. Now, guys, just to quickly go through these isotope questions and this relative atomic mass. So we know that this is working out the average. And I do want to point out a couple of key things here, which is there is more gallium 69 than 71. The relative atomic mass is the average mass of the isotopes, and there is more 69 than 71. Therefore, the average is going to be closer to it. So we're going to do 61, which is its percentage, multiplied by its atomic mass, which is 69. And then we're going to add that to 39.9 times 71, divide it all by 100, and it gives us an average of 69.8, which is closer to 69 than 71. So this answer makes total sense. Just to quickly mention, that's every now and again, what they can do, they give you a ratio. If I give you nitrogen 14 and and nitrogen 15, and I told you that it was in a ratio, it is in a ratio of 3 to 1. And if I asked them to work out the relative atomic mass, I would do 14 times 3 plus 15 times 1, and I'm going to divide 14 than 15. It is greater. Now, what that means is we're going to be really close on the average to 14. And lots of people are going to divide this by 100. Now, if you do that, you're going to get a really tiny number. What you should be dividing it by is 4, which is the total of the ratios that you're doing. So every now and again, it's very rare for them to do this at GCSE. They've only ever done it once. Most of the time they use a percentage because it's more routine. But considering the level of difficulty of this paper, it's not a bad one. Okay, next. Oh, what a lovely organics question. So every single one of these year 11, you guys should be able to recognize. We have ethanol. This is your Friday night molecule. We have, oh, this is a lovely one. Carbon 1, carbon 2, carbon 3. This is propene, and realizing that the ending comes from the, I should highlight that in purple. Let's highlight that in pink and remind you that that's the double bond that makes it an ene. Then we've got methane over here, 1 carbon, and it's an alkane. Then we have cyclobutane, what a lovely one that is. And then we have ethene. You can name every single one of these, and we have pentane. So all of these should be within your realms of naming. Which one is not a hydrocarbon? This is a really clever way of asking the definition. We know, Lucas, methyl propene. Okay, so the reason, Lucas, I will compare propene and methyl propene. So here is try that again. Here is propene. So I've got propene here. Notice that there are 3 carbons and no more. Methyl propene would require an additional, this is propene, it requires an additional meth. Methyl propene, it's actually saying it's exactly the same base molecule, but this time I'm going to have the additional methyl branch. That there is a branched alkene, and that, of course, makes it methane. Question. Methyl, as I said, methyl propene has a branch. Let me know what your question is, Lucas, and I will answer it. It's nice to discuss the difference between the two. You won't have to name any branched isomers, Lucas. You're expected to draw them, but not name them. Okay, so which one is not a hydrocarbon? A hydrocarbon is a compound. So first two marks: compound, hydrogen, carbon only. You must say the word only. Which one does this not follow? And the answer is the very first one. This one does not qualify as a hydrocarbon because, of course, it has the oxygen. Shouldn't do that. That was a rubbish color to choose. Because it has an oxygen atom there, which means it is not carbon and hydrogen only. So P, nice and easy. Next one, really tricky. This again, they're pushing you a little bit further. So they've asked you about compound T. So compound T contains C2, two carbons, and it contains 4 H's. So its molecular formula is C2H4. This is molecular. Now, molecular formulas have a definition. It is the, sorry about that, it is the actual number of atoms, of each element in a compound. Whereas an empirical is the simplest whole number ratio. And we can simplify this, folks. So they've actually made you do 2 clever things in this question. The first thing they made you do is go from the displayed formula. The first thing you're going to have to do is convert that to this is displayed because it's showing all bonds, emphasis on the bonds, all bonds. Then you're going to have to convert that to molecular, which is the actual number of atoms of each element in a compound. And then they're getting you to go over to the empirical, which is to simplify it to the simplest whole number ratio, which is that one. So this paper is pushing you way further. That was a 2-step process, and most students would have been lost at that point. So definitely worthwhile discussion. What is the name of compound U? We know that you have to name up to 10 for your iGCSE. The first 4 are the hardest because those names don't follow the mathematical shape rules. But this is 5 carbons, which is pent, and there are no double bonds, so it's pentane, hence C. Nice and easy. Next one. Compound R, let's quickly jot down what compound R was. Compound R was methane. And it says it reacts with chlorine in the presence of ultraviolet light. Now they do this. So the chlorine reacts with it only in that very specific condition. And what will happen is I will replace one and only one, year 11, one of the H's with a Cl. So I swap that H for a Cl. The other product, if you're interested, is HCl, going to form hydrochloric acid. In fact, it's actually not hydrochloric acid, it would be hydrogen chloride gas. Is this a substitution reaction? Absolutely, of course it is, Lucas. And if they ask you to explain why this is a substitution, so sub-reaction, and they ask why, you're going to say because you are swapping H for Cl. That's it. Not complicated, not difficult. Please, lowercase c, that's not great. There we go. H, that's why it's called a substitution reaction. Right, really horrible question that students don't like. The molecular formula of S is C4H8. Student X states that the compound S is an alkane. Student Y suggests that compound S is an alkene. Comment on each student statement. First mark is student X is correct. Why? Because this is what students missed on this particular question. You have to look back at the compound and you have to state, will there be a point where all the H's are replaced by Cl's, leading to H2 gas and the other compound? Sarah, what a lovely question. You're absolutely correct. If you continue to feed it chlorine gas in the presence of UV light, you will slowly swap all the H's for Cl. But you will never make H2 gas, you always make HCl as a byproduct. Great question. So compound S, the students should have looked at and gone, this is definitely an alkane. And you're going to say why, and that's because it contains only carbon-carbon single bonds. So there's your first one. Compound S has no carbon-carbon double bonds, so it is definitely an alkane. Next, student Y is wrong. Why? Because the student Y is wrong. Why has he said it? This is the hard bit. She said it because the general formula for alkenes is CnH2n, which fits. However, the displayed formula clearly shows no double bonds, which means it's not an alkene. Hard question, that. Any of these comment questions are always tough. Okay, next one. So they've given you some really tough questions right off the bat, and that last comment one really does throw students into a bit of a panic. If you ever get that year 11, just move on to the next one and come back to it. You are good chemists, year 11, and I know this. So if you ever get freaked out, just move on, come back to it. Sorry, come back to it. Next, balance the equation, all relatively straightforward. I'm just going to quickly walk you through it. So I have got 2 hydrogens on the left, 2 hydrogens on the right. We're good. Next, 2 oxygens on the left, 3 oxygens on the right. That doesn't add up. Added 2. And the reason why you added 2 is just to add, all you can do is add another one at this point. So you added another one and you have changed somebody. Am I the only one lagging? I'm not entirely sure what I do about trying to improve the speed of this without I'm trying to think how I can maybe, there we go. That might improve things a little bit. Let's see how that goes. I could try and disconnect and try and reconnect to something else, but that would be, I think that would be a bit of a nightmare. How can I make this a little bit quicker? I don't think I can. See how we go on that one, guys. If it's still lagging, I will try and it's okay. Good. Okay. So I've changed somebody. I've added a 2, right? So if I've changed somebody, I'll start again. Now I have 4 hydrogens, and I've now only got 2 on this side. Added 2. Change, start again. You've made a change, start again. 4 hydrogens now exist. 4 hydrogens, 4 hydrogens. 4 oxygens, 2, 2. We're done. So balancing equations, guys, I'm happy to send you out a sheet with some practice ones to have a go at. They seem to be relatively easy in the exams, but every now and again they do throw in a hard one. Okay, in this, this is the student's method for carrying out this particular practical. They've got this horrible diagram. They're adding a liquid from the, by the way, this is called a tap funnel, and they're going to be adding their hydrogen peroxide, H2O2, from here, which is going to go in down here, and it's going to react with the solid catalyst. We're going to see a whole load of bubbles of oxygen, and the gas is going to appear over there, and we're going to then collect it in the gas syringe, which is then going to move out. And it says, state 2 variables that need to be controlled. Now, the usual rule I always say for students is have a group of these to keep control of. So key things that you should always control: temperature, concentration, volume, surface area, and mass. So which ones apply here? Well, it's said add hydrochloric acid. Volume's out the window. Can't use that. Next one. They measure the time it takes to collect 20 centimeters cubed of gas. Okay. They repeat what with different concentrations. It's just removed concentration from my list. Same. Temperature, surface area, or mass of catalyst. Either one of those would be absolutely fine to say. So have those 5 things, eliminate the ones that they remove in the question, and then choose the ones that are left. Next. Okay, the student makes a different concentration of hydrogen peroxide solution by adding water. This is called diluting. This is called a dilution. And he started off with 10 hydrogen peroxide and 0 of water, and he times how long it takes to make 20 centimeters cubed of gas. And it takes 15 seconds. He then has 8 and 2, so he's diluting it. It takes longer. Fair enough. Concentration decreases. Fewer particles per unit space, therefore fewer collisions, therefore fewer successful collisions, therefore the rate decreases. Explain why he does not do an experiment with 0 hydrogen peroxide and 20 water. Right, sorry, and 10 water. Apologies. Okay, the reason being is, if there is 0 hydrogen peroxide, then there is nothing to be, I would say, bullet point number 1, no hydrogen peroxide, therefore there would be no reaction. First mark. Second one, if there's no reaction, then no oxygen would be produced. If there's no oxygen produced, he's going to be waiting a very long time to reach 20 centimeters cubed of gas. In fact, he's going to be waiting infinitely long. So really lovely question. Students find these really, really tough. I need to put together a sheet for you guys to see those kind of questions. I need to collect them, and I will. Don't know whether I'll be able to get it done before next Thursday, but I'll do my best. Calculate the mean rate of oxygen production in centimeters per second. Now, Y11, if you had me as a teacher, you will recall that I teach you guys moles per dm cubed. And I explained to you guys that this is the unit of concentration. And that slash we say as per, but it shouldn't be. Because what it's actually doing, the per means divide. What that means is it's giving you an equation. To work out concentration, you need moles, and you need to divide it by the volume it's in. And they've done the same thing here. What they have said is centimeters cubed per second. It's told you the equation by giving you the units. So there's my equation. Now I need to find the centimeters cubed. So this is the mean rate of oxygen production in centimeters cubed per second. How much oxygen was made? 20 centimeters cubed. How long did it take at 6 centimeters cubed of hydrogen peroxide? And that was 26 seconds. So we now do 20 over 26 gives us 0.769 centimeters cubed per second. So really clever question. They're checking to see that you guys actually understand what units are and how they can be used and how it gives you the equation. That's really tough. They've never done that before, Year 11, ever. Really clever. Next, they've given you a graph. Lovely question. Complete the graph by adding the scale by labeling the y-axis. 2 marks. This was nice. So the first thing is the first mark was easy. Because if they've got the volume of hydrogen peroxide used, and you look at the data, the other one is going to be the time taken to produce per second. Students, don't forget your units. That's where students will lose their marks, is on the units. The next thing is to realize that if this value here was 75 seconds, and this value here was, where does it come from? The data is 15 seconds. What you can now do is figure out what all the rest is. So it started off at 0 and it was going up in tens each time. Really tricky, that required quite a lot of thought. Next, in an experiment, a student using 4 centimeters cubed of hydrogen peroxide and 6 centimeters cubed of water. Right, 4 centimeters of hydrogen peroxide, that's there. Right. So next, it then says, use the graph to determine the water collected, the time taken to collect it. What did she do? The student did not close the tap funnel. Plot the point on the graph to show the possible result. Right. So this one required some serious looking at the diagram, because here's why this is tough. You guys had to realize that the gas that's being made in the conical flask, the gas that's being produced, the bubbles that are being made that are escaping up to here, you have 2 outputs. You've got one going to the tap funnel and one going off to your gas syringe. If you forget to close the tap funnel, the gas is going to be split. We're going to have some gas disappearing up the tap funnel and some gas going into the gas syringe. What that means is it's going to take a lot longer to fill the gas syringe because some of it will be going up the tap funnel. So you then have to look at 4 on the graph. This was so hard question. Increasing concentration increases rate and yield. No. Why would you say it increases yield, Kayan? Yield is more to do with equilibrium, not to do with rate of reaction. If you increase concentration, it could very well be already in excess, which means you won't change the yield anyway. Yield is specifically for equilibrium. Don't use it in a rate setting. Whereas increasing volume only increases yield, right? No, like be careful. You've mixed rates and yields together, and rates and equilibrium together. Be careful. If they increase the concentration, you will increase the rate, but you probably won't increase the yield. If you increase the volume, then you're not going to increase the rate. You are simply going to increase the amount outputted by it if it's not already in excess. That requires a bit of that requires a question context, Kayan. I've got some questions which I'm happy to chat through with you if you pop into school, and I'll go through them with you. So we had to go any plot. We had to realize that 4 was on the graph. This is where we were expecting it to be, but half the gas is going to go up the gas syringe and half the gas is going to go up the tap, so it's going to take a lot longer. So the time, it just needed to be anywhere above that line. Really, really tough. Next, a solution containing 5 centimeters cubed and 5 waters is decomposed. Use the graph to predict the time taken. Right, read it off as you'd expect. 5 on the graph is here. Read it up until you hit the line, read it across, and read off your value, which was 32 seconds in this case. Be really careful on reading your graphs, year 11. They don't give you much room for error there. Make sure that you're using a ruler. Okay, the original hydrogen peroxide was labeled as 10 volume solution. A 10 volume solution produces oxygen 10 times greater than the volume used. So what that is saying is that if someone gave me 10 centimeters cubed of hydrogen peroxide at 10 vol, it will make 100 centimeters cubed of oxygen gas. That's what it's saying to me. We can do a slightly harder one because it's just times 10. If I had 5 centimeters cubed, then I would produce 50 centimeters cubed of gas. If I had a solution containing 1.2 centimeters cubed, I would produce 12 centimeters. I'm just multiplying it by 10. It's not complicated. It then says suggest, and every time these suggests come up, it's hard. We know this. Suggest what might happen if the student used more than 10 centimeters cubed of gas. It required you to once again go back to the diagram. The gas syringe says very clearly it holds 100 centimeters cubed of gas. So if you add 20 centimeters cubed here, you're going to push that gas syringe, you're going to push the plunger right out, and the gas syringe will not be able to measure it. Tricky question, all about the diagram. Everything comes back to the diagram, year 11s. Remember, in your real exam, if they give you a diagram of an apparatus, a lot of the answers are going to be there. He would produce more than 100 centimeters cubed of gas. The gas syringe is unable to measure above 100 centimeters cubed. So the gas syringe plunger would fall out. Third mark. For the other question, if they didn't turn off the tap funnel, wouldn't there also be like more H2O in the flask? So wouldn't it decrease the time taken? Right, Tiffany, number 1, if you add more, you won't make it faster. You just make more at the end product. Remember, we learn the 5 factors that change rate. Rate is affected by temp, by concentration, by a catalyst, by pressure, by surface area. Notice, nowhere on this list is vol of X. You can add as much as you like, and you won't make it faster. You'll just make more of it. Be careful. You're absolutely right. If they added the hydrogen peroxide, you make the assumption that in the diagram that they're adding 10 that they're only filling up the tap funnel using 10 centimeters cubed. Yeah, you have to make a big assumption there, which again makes it really hard. Next. Okay, so this one dropped into our good old friend dot and cross, and there seems to be also, if you give a random transition compound, how do you know what color it is? Ah, that was weird. Well, you need to know copper 2+ is blue, iron 2+ is green, and iron 3+ is brown. The rest of them, you don't need to know. They'll tell you. Done. That was a random question, okay? You don't. They'll tell you. Next, dot and cross. So, guys, first thing I need you to focus on, and don't forget, U11, I can tell you what's going to be on your paper, and this is going to be one of them. Lithium is a metal. Oxygen is a non-metal. Yeah, what this means is it's going to be ionic. Don't, please don't start doing these diagrams, because that is non-metal, non-metal. This is metal, non-metal. It needs to be ionic. The next trap, of course, in this particular question was that they asked you to show the arrangement of the electrons, which means you had to remember that all electrons must be shown. Students often say, but why is copper 2 carbonate green and copper 2 oxide black? This came up in the past papers, Kayun, because you have to know that. It just is. I can't give you an answer to that at a GCSE level. You need to know certain colors, and those colors you need to know. Copper 2 oxide is black. Copper 2 carbonate is green blue. Nightmare. So guys, students are asking me, because of this one particular question, they're saying, when do I show, and I'll write it down, when all shells. They're saying, when do I draw all of them, and when do I draw just the outer? Guys, I can give you the answer to that question, because later on in this paper, look what they asked you. Show outer electrons only. So don't say it. All electrons are needed, U11. All of them. So bear that in mind. Next. So, okay, next one. So, guys, you know this. You know that the lithium, they've given you everything in your diagram. We know that lithium is going to give its outermost electron over, let's do it in pencil. That electron's going to go over to oxygen there. This one's going to go there, and we're going to form an O2 minus, and notice our dot and crosses. Yeah. And the lithiums have lost 2 electrons. Next. Right, again, really hard question, because it gave you a formula which you wouldn't expect. That's really tough. So to realize that they've given you, number 1, let's read the question. 1.38 grams of sodium is burnt in oxygen. The product of the oxide is a mass 2.34. So they've just told you sodium, mass this. Sodium oxide, mass this. Calculate the empirical. Now, you guys, I have trained you well. As soon as you see the words empirical, you break up it into elements, sodium and oxygen. Mass of sodium was given in the question. It was here. However, the mass of oxygen was not. You had to do the mass of the oxide minus the sodium at the beginning, to give us the mass of oxygen for that step. So the first mark was that bit. So then you run your normal process, divide those masses by the relative atomic masses from the table. Sodium is element number 11, mass 23. The mass goes in here, grams over rams. This is the mass of oxygen. Oxygen, of course, is 8 and 16. It's mass 16, drops in there, grams over rams. We get our moles. Moles counts particles, counts atoms, counts molecules. And we get the same number. You divide them all by the smallest, and we get 1 to 1. And that's our ratio. So our formula is just NaO. And of course, the reason why this is hard is because anybody, any year 11 who I have trained well, would recognize sodium oxide as that. This is not normal. Yeah, this is rarity. I checked that 5 times because it looked weird. Lucas, I totally get it. Edexcel pushing you really outside your comfort zone. And it's really, really tough that. I don't know what to say apart from the chemistry. Yeah, you're a good chemist. One of the best. Be confident. I know you can do this. You can do it well. The next thing. The oxide has a relative formula mass, right? They've told you that we've just worked out the empirical as NaO. This is the simplest whole number ratio. And they've told you that the real thing weighs 78. Well, how much does the simplest version weigh? Well, sodium's 23 and oxygen is 16. The weight of the simplest one is 39. And they have just told you that the real one weighs 78. Well, if you realize that the simplest weighs 39 and the real one's 78, divide the bigger by smaller, and you realize the real one is twice the size. So you double the little numbers. I seem to find some students doing this. You're not allowed to do that. That just says 2 of them. You need to change the numbers in the formula. Right, next. Horrible question. It says potassium can react with oxygen to form potassium superoxide, KO2. The equation shows the reaction of the oxide with water. Complete the equation. This was really clever. Right. 2 potassiums go in. No potassiums come out. We need 2 potassiums. Now, the habit here will be for students. Students will commonly go K2. You're wrong, because if you now double the 2 on the outside, it becomes 4, which means they only wanted 1. Hard that. Next, how many oxygens have gone in? I've got 4 oxygens in total, because of that and 2 there. And I've got 4. Oh, hang on a sec. Sorry, I apologize. I've got, really wish this behaved. I have got 4 oxygens here, and I have 2 oxygens there. Don't like doing that backwards. 4 O's and 2 O's. That's 6 in total. Well, over here I've got 4. We need another O. We need 2 of them, and that 2 multiplies it. Well, how many H's? I've got 4 H's here and 2 H's here. I'm missing 2, so the last one is the H. The habit that students have here, which, oh my God, guys, this is so hard, is that people are going to do that. But the problem is when you now multiply them by that big number that's there, you now get double the numbers. That was really hard. Also, if you ever put any group 1 metal into water, it will form an alkali solution. It's a metal oxide, so KOH was the right choice. Hard question, though. Really hard. Next. Oh, calculations, which was pure evil. Okay, they've given you the equation. You're going to need it, folks. If they give you an equation, you're going to have to use it. So, first bit, 5.5 million tons of carbon dioxide. Right, 5.5 million tons of him are released into the atmosphere each day as a byproduct of extraction of iron. Oh my God, that's terrifying. Calculate the mass in tons of potassium superoxide. So they're asking me about this guy. How much of this guy do I need to react all the carbon dioxide? Right, so the first thing I need to do is work out moles. To use an equation, I need moles. My moles is grams over rams. Right, so I haven't got grams. I've got 5.5 million tons. Well, I'm just going to use, because if you notice what the output is, it's in tons. Oh, but it's not in the millions of tons. Oh, dear. Problem. Y11, I've just made a mistake. That's how hard this paper is. There's an error that I have just said. So the first thing is, I need to realize that this is given to me in million tons, and that's just spitting out in tons. So I've just made a mistake in my final answer. So what I need to do is I need to convert that 5.5 to 5.5 million. So I'm going to add that in there. There we go. So now I'm going to have to change my calculation. Grab my calculator. So I have to have the same things. So that's now 5.5 million tons. So I've now got 1, 2, 3, 4, 5 zeros divided by 44. Right. So what does that now give me? That's now the wrong answer. I lost a mark. 125,000. Right. That's carbon dioxide. I'll write that under there. 125,000. How do I now get to the superoxide? The ratio up here, the ratio is 2 to 4. So the ratio here is 2 to 4. That's the same as a 1 to 2. So that's a 1 to 2 ratio. To get from here to here, I've got to double it. So I double it. Ratio 2 to 4. So I'm going to times it by 2. Now, my calculation now, of course, is wrong. 125,000 times by 2. I've already got the number on my calculator. That gives me 250,000. Oh, 250. Horrible. 1,000 tons? Right. That now is the moles of potassium oxide. We're not even finished yet, folks. That's now the moles. 250,000. How do I now get to tons? I've got to now reorganize grams over rams. Moles is grams over rams. I've always got the rams, and I've just worked out the moles. Number of moles times by rams gives me grams. Right, so 250,000 multiplied by the relative molecular mass of KO2. Is that the right formula? Potassium on the periodic table is number 39. Oxygen is 16 times 2. 39 plus 32 gives me 71. So now multiply 250,000 times 71 gives me, holy mackerel, an enormous number. So my answer's wrong. I got it wrong, guys. In the exam, I would have got that wrong. That's hard. Even I'm making those mistakes. 17,750,000 tons. What a nightmare. It's massive. Horrible question. I really hope they don't make you have to do those kind of conversions, because if they do, that's tough. Next. My laptop is just struggling a bit. Okay, next. Okay, now luckily those people who've been attending my revision sets will recognize molecules like this one, and they have given you a molecule that's combining two functional groups. So we have number one, it is an alkene, and it's also an alcohol. So it's got 2 carbons. Let's count my carbons. So it's got 2. So this is eth, meaning 2 carbons. 2 carbons. Next, it is an ene. So that is ethene, and it is an ol. You can't put ethene. You can't put an e in there because EO is horrible. So there's ethenol. Tricky that. Next, explain the color change observed when bromine water is added. Bromine water, you've got to know this test, folks. Bromine water, of course, is orange. So if I change my color, if my laptop behaves itself, which it really isn't. Orange. Bromine water is orange, and it's going to turn colorless. Orange to colorless because bromine reacts with the carbon-carbon double bond. Next, draw the repeating unit. Again, I've been doing this in my revision sessions. It doesn't matter what they give you. It doesn't matter if they give you something you have never seen before. I could put the word monkey on here, and I could put the word Steve on here, and the word Mr. Duncan on there, and I don't know, X. And then they say, draw the polymer. 2 carbons, line and line, because the only 2 that matter are those 2. The double bond breaks, and now put the people on X, and Mr. Duncan goes there. This one has the word monkey on it, and this one has the word Steve. Doesn't matter what it looks like. Just put it together, break the double bond, and add the people that you need to. Next. Oh, I've never seen a typical molecule of PVA. We know that PVA is a giant structure of repeating units. And they've told you its relative formula mass is 27,500. Calculate the number of repeating units. Right, well, if the repeating unit was this guy, how much does this guy weigh? My laptop is really, always struggles about this time. So I've got carbon 12, 12, 1, 1, 1, 16, and 1. How much does ethenol weigh? 24, 25, 26, 27, 28, 28, 30, 44. So that molecule there has an MR of 44. Well, if you take millions of those, or in this case, hundreds, take hundreds of those and join them together, you're going to create something with an enormous MR. How do you work out how many went into it? The total MR, so this is the total for the chain, repeating chain. This is the weight of one particular piece. Divide the huge chain by the small piece, and it tells you the number of pieces. But you had to make this. Why was this so hard? Because you had to make the leap of understanding that you could work out the MR of the monomer and then apply that to the polymer. That's hard, folks. Never seen them do it. Pure PVA melts at 200 degrees Celsius. State how the melting point of an impure sample of PVA, it would be lower. Now, the reason being, I'm not going to go into the melting point. Just remember that if you have an impurity, it will always lower the melting point. Next, Mingfan is used in Chinese medicine. It is a mixture of substances, including a compound called alum. The first test is a flame test. What color will potassium ions produce? Nice and easy, folks. I like it when they give us your chemical test. You've just got to know them, folks. If you don't, you can't make it up. Next, in a second test, she adds a solution of sodium hydroxide. Write an ionic equation for the formation of aluminium hydroxide. And they've told you everything you need to know right there. So we're going to be adding aluminium 3+ plus 3 OH minuses, and they're going to join together to form AlOH3. Clever question that. Includes 8 symbols. Everybody is aqueous apart from the precipitate because they tell you. Clever that. Not recognizing what they have got. What a massive test. Can I say that aluminium is solid? No, because aluminium ions are not. It contains a solution. Great question, Dana. All solutions contain ions. It's not so. Aluminium metal will be floating at the bottom. Sorry, it wouldn't be floating, it'd be sinking. Next, third test is for a sulfate ion. Just know your tests. If you don't know your tests by now, guys, you need to seriously get on it. Test for a sulfate ion, add hydrochloric acid, 1 mark, followed by barium chloride. I'm actually adding the word solution, and you will form a white precipitate of barium sulfate. It is insoluble. Next, super hard question. Year 11, when I taught you, when I was teaching you guys metal extraction, I mentioned a compound called cryolite. Now, cryolite is sodium, aluminium, fluoride. And I explained to you guys how I remember that formulae. The reason being is because sodium is +1 and aluminium is +3 and F is 1-. In order for me to cancel out all of those positive charges, I'm going to need 4 Fs. They've done the same thing here. They've realized that I have got a K+, an aluminium 3+, and a 2- there. Well, if I have just 1 of each of those, then I have a total of +4. To cancel that, I need 4-, which means I need 2 of the sulfate. That's hard. Next, if you didn't get that, you were absolutely stuffed for the next one. Calculate the value of N for the water of crystallization. So if we had 1 potassium and 1 aluminium, and then we worked out the weight of a sulfate ion and times that by 2, you can work out the total MR, the weight of KAlSO4, and the weight of that is 258. And it then told you that KAlSO42.NH2O weighs 474. Well, now I can take away the mass of that from this, and I'm going to get, at that point, I get that minus 258. Sorry. Is that right? Yeah, sorry. Minus 258, which will give me 216. And all of that is water. How much does water weigh? Water weighs H1 times 2 plus 16. Water weighs 18. How many waters are in 216? 216 divided by 18 gives you 12. This is so hard. The level, if they did that, folks, If students didn't get that one, you ain't getting the rest. You're going to lose the rest. That's tough. Couldn't believe how far they pushed you, but great chemistry. Next, use the information in the table to predict bromine. Right, all you did, folks, was you draw your line. That's minus 35. That's 184. What is the difference between the two, which is just over 200? So the difference there is 200. So halfway would be a difference of 100. Add it on to that, and it's about plus 75. So very straightforward. If you ever get data of A, B, and C, and I'm told you that's 10, that's 200, and that's 330. What's B? Work out the difference, which is 320. Divide it by 2, which is 160. And add it on. That's 170. Clever. Next. Right. Again, tough question. So this time, waiting for that. Fluorine is above chlorine in the group 7. Predict the color and state of fluorine. Fluorine is a pale yellow, but they would also accept colorless. If you see the pale yellow, you're probably about to so yellow or colorless, and the state is, of course, a gas. It's getting darker as you go down the groups. They've done a clever trick of going up. We know that usually we do this, which is green, gas, brown, liquid, black, gray, solid. The melting point's increasing, so the top one's going to be gas, it's going to be paler than green, yellow. I think they probably also accepted yellow. Next. Okay, looking at the equation. Explain why this reaction is described as a redox. Right. So iron in this particular question is +2. And it is going from iron 2+ to iron 3+. It's lost an electron. Because electrons are negative and it's lost it. It's going to become more positive. So each iron 2 loses 1 electron. This is oxidation. Oil. Next, bromine goes from 0 to -1. Oh, that's gained an electron because and reduction is gain, and both happen at the same time. Every year this appears. Be aware of it. They also do it in the setting of oxygen as well, so do watch out. Next. Other elements in group 7 may also react with iron 2+. Describe an experiment to find out if chlorine reacts with Fe2+. You should outline a method. So at this point, keep it simple, don't overthink it. They've outlined a method, test for reaction, and safety precautions. Right, so I'm going to have a solution of iron 2. So I'm going to take a sample of iron 2 nitrate. Guys, you notice that I choose the nitrate and I include the Roman numeral. The Roman numeral must be there because and I choose a nitrate because all nitrates are soluble. I'm going to bubble through it chlorine gas or add chlorine water, either one. And that gives me the method question. I'm going to leave it then for a few minutes. I'm then going to take a sample and add sodium hydroxide. Sodium hydroxide tests for iron 2 and you form a green precipitate, PPT. And it also tests for iron 3+, which is a brown PPT. So if the green precipitate forms, then the chlorine didn't react with iron 2. Precautions. Sodium hydroxide is corrosive. Wear gloves and goggles. If you could also say chlorine gas is toxic, use a fume cupboard. Either one. Next, into covalent diagram. I came to this earlier. So the first thing to realize is you guys never put Cl with oxygen, and it's tricky this because you've never seen it, but the first thing to do is to translate it into a picture or a stick diagram, as I often call it. Chlorine is in group 1. They always make 1 bond. Oxygen must make 2, and there's 1 oxygen which means it's at the center. I drew it out as sticks. Then I translate that diagram. I'm tempted to give you another one to show this in action. So let's say we had H2S. No one's ever seen it before. It's called hydrogen sulfide. It's a bad egg smell. First thing to do is just realize that S is at the center and it's joined to 2 H's. How many bonds does S make? S makes 2 bonds because it's in the same group It's in the same group as oxygen. So oxygen here is in group 6, and oxygen, we all know, makes 2 bonds. Sulfur is in the same group. It also makes 2 bonds. So we now have this picture, and hydrogen makes 1. This makes sense. Right, now we turn that into the circle diagram. Circle, circle, and circle. There is one bond for each of those, which means I have a dot and cross in each gap. That represents 1 bond. Now make everybody add up to 8 except hydrogen. So hydrogen are done. But now we have to make sulfur add up to 8 by adding on the extras. So same thing with the chlorine oxide here. We've got Cl2O. Oxygen is at the center. It forms 2 bonds. Chlorine is in group 7. It makes 1. Draw the picture. Circle, oxygen at the center. Show the overlap. Right, it's a single bond. If it was 2, there'd be 2 pairs, but it's 1, so there's 1 pair. Make everybody add up to 8 except hydrogen. Well, none of these are hydrogen, so add on every to make them equal 8. Hard question, because you've never seen it before. Didn't even know it was possible. Next. Chlorine oxide reacts with water to form a solution. Suggest a value of the pH of the solution. Give a reason why. Right, it's pH 1. It is a covalent oxide. You guys learn that SO2, sulfur dioxide, SO2 is acidic, causes acid rain. NO2 is acidic, acid rain. pH 1, pH 1. They're all acidic. As soon as you see a covalent oxide, it is acidic. Next, give a reason. It's covalent oxide, so suggest a pH, pH 1. You're done. Next. Right. So we're testing the percentage of oxygen in the air. We've seen this one before. They've done this in the past. So the teacher sets up the apparatus to record the volume of gas. When the level of water becomes constant, he records the final volume. Suggest the time taken. You guys need to know this reaction. Just a week. You've just got to know it. Can't make it up. Takes ages for things to rust. Other than the changes in the levels of water of the apparatus, take one other observation. The iron wool will turn brown as it rusts. Next. The teacher adjusts the apparatus before recording the volume of the tube. Explain the changes he makes. That's horrible. You've got to look at this picture and go, what is wrong with this picture? And the answer is, you can't take that reading. You need to have that vertical so that the level of water is in line with the scale. Not complicated, but really tricky because you've got to get that from the picture. Stands test vertical, so the level of water is horizontal, but the scale can easily be read and read correctly. Next, the teacher does the experiment 4 times. Shows the results. Calculate the percentage of oxygen in the air in the first experiment. Right, so they started off with an initial volume of 32, the final volume of 26. 26 over 32 gives 81%. Now here's the problem. That is the left over nitrogen and other gases. How much oxygen was used? 100 minus the answer. So this is making you do an extension calculation. Everyone is going to get it wrong. Tricky, watch out. Next, although the mean percentage of oxygen in the atmosphere is 19%, the teacher states that the value may not be accurate. Comment on this statement. Well, the first thing is to state that there is actually 21% in the air change. That is what it is. Maybe not all the oxygen has reacted. Maybe the temperature of the reaction was not consistent during the readings. We know that temperature affects the volume of gases. So, clever question, be tricky. Next. Explain the effect, if any, on the calculation of percentage of oxygen when these changes are made. The wool is left for a shorter time. The percentage will be lower because there won't be enough time for the rust to be completed, so there will be leftover oxygen that is unreacted. The value will be lower. A larger piece of iron wool was used. This won't make any difference because it is stated already in the question that they're going to use excess from the diagram. There it is. Excess wool, you can add as much. I said some gas was the water. Oh, nice. Donna, you're wrong, but it was a great effort. The reason being is it'll always dissolve into the... Oh, hang on a minute. Although the mean percentage of oxygen in the experiment is 19%, teacher states that the value may not be accurate. Comment on this. Some of the oxygen dissolves in the water. Donna, I completely agree with you. So the final volume will be less than the actual volume. I completely agree. I don't know if it's not on the mark scheme. It might be. I'll check it, but what a beautiful answer. I think it's a great answer. Well done. Great chemistry. I'd have given it to you in a real exam, but it'd be interesting to have a look at the mark scheme. We'll do that tomorrow, Donna, me and you. We'll check that. Great answer, though. No, the extra iron won't make any difference since it was already in excess. Next. Whoa, what a mess. Crude oil can be separated into different fractions. These are used for fuels, yada, yada, yada. Which hydrocarbon is an isomer of this carbon? This compound. Guys, you just had to count the carbons. I thought this was really clever. Pentane, of course, is C5H, double it and add 2. 12, does it fit that? No. Hexane, C6H, double it and add 2. 14, does it fit that? No. Heptane, C7H, double it and add 2. 16, does it fit that? No. Okay. C8H, double it, 18, and it does fit. So, the last one. It's not on the mark scheme. Donna, that's really interesting it not being there, because I think your answer is really, really great chemistry. And I totally think it's like the mark, and I think you'd probably get it in a real paper because it is good chemistry, and I feel like they should be accepting it. Next, another gas is the largest component of car exhaust fumes. Oh, this was so cheeky. A car exhaust contains a number of different gases. Water vapor, carbon monoxide, the gases where the fuel burns in the engine. Identify the gas. Oh, it was so mean. Nitrogen. The reason being, guys, there's 71%. No, there isn't. There's 79% nitrogen in the atmosphere. That you're going to have it. The nitrogen goes in the engine and out the other end. That was so evil. Car exhaust fumes also contain some nitrogen oxide. State 1 effect. It causes acid rain. Mentioned that earlier. Next, why can car fumes contain carbon dioxide and carbon monoxide? Right, guys, I thought I'd flag this because I missed it. Carbon monoxide is produced by incomplete combustion of the fuel. CO2 was already in the air. That's what I wrote down, and it was wrong. To really consider my marks there. So the first thing I would have said is, explain why car exhaust fumes contain both carbon dioxide and carbon monoxide. So number one, I would say complete combustion of fuel results in CO2. Incomplete combustion, by the way, I wrote this down and it was wrong. Incomplete combustion of fuel results in carbon monoxide. One mark. And so the next thing is, why do we get both? Because some fuel burns completely. Some fuel burns completely, others not. Others not. Really horrible. Mean. Carbon is a solid. Carbon is not a gas. That is correct, Lucas. That is carbon particulates. They cause global dimming. Thought that was a really, really clever question, that one. Just so mean. You guys learn about complete and incomplete combustion, but you don't realize you're not taught that they can occur simultaneously. What a mean thing for Edexcel to do. So mean. But really what they were asking is, this question was saying, if I get rid of that, the question is saying a car fume contains both carbon dioxide and carbon monoxide. Explain. So they're saying, explain where the carbon dioxide comes from, complete combustion. Explain where the carbon monoxide comes from, incomplete combustion, because there's not enough oxygen. And then they're going to say, why do we get both of them? Because that is occurring at the same time. Really, really mean. Next. Once again, not done particularly well in lessons, and I'm included in this, folks. There are many different types of crude oil. Crude oil, which is more valuable than others, depending on the mixture of liquids they contain. So it simply said, discuss the Brent crude oil and Maya crude oil have different prices. Use the information from the above diagram in your answer. Right, so the first thing is you need to say, is Brent is more valuable than Maya because, First thing you should always say. So why? Because Brent contains more of the gasoline fraction than Mayer. 1 mark. Tick. Right. Also, Brent also contains more refinery gas than Mayer. The next thing is that Mayer contains much more fuel oil and bitumen than Brent. So you're going to give 3 examples, and then, of course, state that the gas and refinery gas are worth an awful lot more money than bitumen is. Clever question. Brent oil contains a larger percentage of gasoline compared to Mayer. Gasoline is more valuable than the other fractions. Mayer contains larger percentages of fuel and bitumen, which is worth less money. We're done. Missed mark. Oh, isn't that fascinating? I missed one. And chances are the reason being is because I've just not gone far enough and given enough examples. So recognizing that they're also more useful, they're more valuable, they're worth less money because they're not, bitumen is not used as a fuel, only for road surfaces. Be interesting to look at the mark scheme for that one, pick up that next one, but I definitely missed one. Next. Right, draw a diagram. Describe using labeled diagrams how and a simple diesel fraction can be cracked into gaseous alkenes. You had to draw it. Please remember, folks, these practicals, they can ask you to draw, and that was tricky. Cotton wool soaked in diesel, heat that as zeolite catalyst, bubble it underwater. Tricky. I didn't even write any words for that, didn't need to. Next, most silver coins do not contain silver, but are made from a mixture of other metals. Describe the difference between a compound and a mixture. 2 marks for 2 definitions. A compound is when 2 or more atoms are chemically bonded. A mixture is when 2 or more substances are in the same container but not bonded. Seems very reasonable. Just them waffling to get you to give 2 definitions. They haven't asked many definitions up till now, so very reasonable. Next, so which type of salt is formed in this particular reaction? Hydrochloric acid. And what's the coin made from? Well, it's going to form a nitrate, of course. Oh, hang on. Sorry, I said nitrate. Hydrochloric acid is going to form a chloride, of course. So reasonable. Students state that there is no magnesium on the surface of the coin. Explain why she is correct. If, and this is hard, guys, I wrote that and only got 1 mark because the mark scheme said that I needed to say that compounds are in fixed positions. Oh. Most silver coins do not contain silver, but are made from mixtures of other metals. That's different than a mixture. A compound is where 2 or more atoms are chemically bonded. A mixture is when there are 2 or more substances in the same container but not chemically bonded. Lucas, I wrote that and only got 1 mark because the mark scheme said I needed to say the compounds are in fixed positions. That's complete rubbish, Lucas. Like, the mark scheme's wrong there. That's horrible chemistry. It doesn't make any sense why you would mention that. Do you know what? I'll have a look at that later and I'll get back to you. But that's a very, very odd thing for the mark scheme to say. I'll look at that and I'll check it. Hydrochloric acid always makes a chloride. We know this. The next thing, this was really hard because you guys had to know that if you add acid to magnesium, you will see fizzing because the magnesium will react with the hydrochloric acid to make hydrogen gas. And you will. In this case, explain why she is correct because we did not see any bubbles. And if you saw no bubbles, then we didn't make any gas. And if there was no gas, then magnesium can't have been there. Magnesium would have reacted to form hydrogen gas. Bubbles would have been seen. Clever question. Oh, chromatography appearing again. The spots on the baseline are made as small as possible. Suggest a reason for this. If you ever do this, and you guys will have done this in year 7, if you put a massive splodge and a splodge, when the water level rises, what happens is that we know that they blur outwards as they go up. And what will happen is they'll end up overlapping. And so we always make them, fixed compositions. Ugh. Even more bizarre. So I wouldn't worry about it, Lucas. I'll go and see me tomorrow about it and we'll have a look. Big spots would merge together, which is what they would do. And then it's hard to tell what color comes with what. Next, state why the spot containing Fe2+ stays on the baseline. It is insoluble. Easy enough. The iron 2+ salt is insoluble in solvent. Explain which metals are present in the coin. Right, so this one's just a comparison. So this one now, of course, simply is saying, right, so in the coin, we've got him and him. Where do they match up? I've got copper 2+, and I've got nickel 2+. Nice and straightforward. And explain your answer. They have traveled the same distance. Nice, that one, as the Fe2+. Does this bring us to the end of the paper? I think it may. Is that end of questions? It is. Right. I said, so the spots don't soak down, you know, due to gravity. Ah, Dana, no, that's not true. If you can put as big a spot on as you like. See if I can go back to this and unshare my screen. Y11, thank you so much for coming along, guys. Just to finish off my explanation for Dana. Dana, it doesn't actually matter how big the spots are in terms of gravity pulling them down. As long as the spots are above the line and the solvent moves up the paper, it will travel up the page. So they won't actually drop down if you make the spots bigger. But of course, if you've got multiple spots on a page, you need to make them as small as possible because they tend to wander. The spots tend to actually kind of bend like this depending on the curvature of the paper. So we make them small, so if they travel, they tend to travel in a straight line and they don't blend together. So multiple questions, but guys, I hope you found the paper useful. It was a really, really hard paper, and I know that it, hopefully for the people who got to see this, it should be really good value. Because guys, if you're going through this and realizing that you understand the principles that are being asked you here and all the questions that I've gone through kind of make a bit more sense. If you can cope with this, guys, you can do anything. So I'm really, really proud of how hard you're working. Keep doing it. And if you have any further questions, don't hesitate. I love you. See you soon.